SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The title of today's topic is Geo-distributed cloud data centers. Geo-distributed cloud data center, interaction of data center with the users and with other data centers. We will also describe the data center interconnection techniques such as traditional schemes such as MPLS, cutting edge such as Google's B4 and Microsoft Swan architectures. So, let us see about the inter data center networking. What is the problem? In today's virtual use of any popular web application means to communicate with the server in the data center. Take this example, the user is using in the browser www.google.com. when he types in their browser over here, then this particular web application will open the client and the browser will also initiate the connection with the server. So, the server application is going through the internet and it enters into the cloud data center. Now, there may be many cloud data centers available. Out of them, one of these particular data center will serve this particular application as a server. So, this particular traffic which enters into the data center, now data center will experience all such traffic which is coming from different web browser or from the user. They are called northbound traffic. This northbound traffic then accesses the servers inside data center. So, more than one servers will be accessed and this generates the southbound traffic. Inside data center. So, northbound traffic will trigger into the southbound traffic into the data center and then that particular server will then respond back the replies to the client. Now, this is what we are now discussing over here, that the virtual use of any popular web application means to communicate with the server and that is called the data center. So, data center we call it as a server in a client server architecture. However, the connectivity for this particular service depends upon the internet. So, this is this connection, this and inside. So, this particular connection which connects not only to the client, but also different servers, different data centers is all internet dependent. So, the connectivity for this particular service often depends upon the internet. So, internet becomes crucial in the application service performance. So, the data centers also communicate with each other over the internet. For example, here these data centers, let us say one data center resides, let us say in US, the other data center resides in India and they often communicate with each other through the internet. So, data center also communicate with each other over the internet, that is replicating the client's data across multiple data center. This is one such example of an application. So, in the cloud scenario, the wide connectivity, wide area connection or the internet is as crucial as the data center infrastructure. So far we have seen the data center infrastructure, which is nothing but it is a 3-tier hierarchy over which several servers are connected. So, besides this, the other connectivity which we have not talked about is about the wide area network. So, this wide area network or the internet is as crucial as the data center infrastructure. So, we are going to discuss in this particular discussion, that is called inter data center networking, which is nothing but a wide area connectivity which is required to connect the data centers or to connect the clients to the data center through the internet. This is all requires the wide area networks. So, why multiple data centers are there? Why multiple data centers are needed? So, why does the service provider like Google often needs an extensive infrastructure, so with so many locations across the wide expanse of the globe, that is geo distributed data centers. So, why so many distributed data centers are required across the globe? Even the Google also does that. Google, Microsoft, Amazon all have geo distributed data centers, that is multiple data centers, not at one place, but at different place across the globe. So, the reason is the following. First reason says that better data availability. That means that if one of these facility goes down due to some reason, whether it is the natural disaster, still you could have your data available at other locations if it is replicated. So, that means the data is replicated in such a way, so that it should reside more than one such places in because of multiple data centers availability. Second important reason is called load balancing. So, multiple facilities can spread the incoming and outgoing traffic over the internet across a wide set of providers over a wider geographic regions. So, that is why it is called the load balancing. Now, third important thing is about the latency, that if present in the multiple parts of the globe, then they can reach the client in different locations at a smaller distance and thus reduces the latency. So, multiple presence has the following advantages which we are now seeing up, that is better data availability, load balancing, latency. Fourth one is about local data loss. So, several authorities might require that the companies store the data from that company in that jurisdiction itself. So, these particular laws affect how what kind of rules and regulations for data. So, those kind of laws are called local data laws of different places across the globe. Finally, the hybrid public cloud operations. So, this can handle the average demand from for the service from the private infrastructure and then offload the peak demand to the public cloud. Now, let us see about the traffic. So, there was a paper published in 2011 in Infocom conference titled "A First Look at Inter Data Center Traffic Characteristics via Yahoo Datasets." So, this particular paper has shown what kind of data center traffic is being experiencing, and that is good enough to design the inter data center networking. So, studies from 5 Yahoo data centers, that is from 2011, and this study is based on anonymized traces from the border router that connect these data centers. So, this particular figure shows 5 major Yahoo data centers and their network connectivity. So, you can see that these are different locations: Hong Kong, DCP, PODAX and UK, and you know that their border routers are shown over here and they connect. Now, these are inter data center traffic. How this particular traffic is moving across the data center is going to be an important observation results, which is expressed here in this particular paper, which will show you the requirement of these kind of inter data center traffic. Now, here this particular traffic is shown in two different figures, and this shows that the number of flows between the client and the data center. Okay, so the client and the data center traffic is shown over here in this particular diagram. So, on the right, between the data center themselves, the 3 lines on each plot are of 3 different data center locations. Notice that y axis on these 2 plots are different. In terms of number of flows, the traffic between the data center is 10% to 20% of the traffic from data center to the client. So, here you can see that this particular flow between the data center could be very long lived and carry more bytes than those between the clients and the data center. So, here you can see that the data center to the client flow pattern is shown over here, the number of flows, and here you can see across different data centers 1, 2, 3, 3 different data centers are shown. Similarly, you can see that whereas data center to data center traffic pattern is shown here over here about the number of flows. So, you can see here on that the y axis on these 2 different plots are different. Here the number of flows is 5 and 10 multiplied by 10 raised power 6, and here 0.5 and 1 multiplied by 10 raised power 6 are different. So, in terms of the flows, the traffic between the data center is only 10 to 20%, you can see, of the traffic from data center to the client. So, DC to the client has more traffic, more number of flows experienced compared to the data center to the data center traffic flow, and this particular data center to data center, that is only 10% of the traffic compared to data center to the client. So, data center to data center traffic is little, means only 10% compared to the data center to the client here in this case. The flows between the data center could live very long lived and carry on more bytes than those between the client and the data center. That is another important observation. Now, why are these networks different? So, it is persistent, dedicated tens of gigabits per second connectivity between a small set of endpoints. So, here you can see that the wide area network, why it is needed is because of that private wide area network is required, or let us say the internet can still be used over here. So, if it is being a private wide area network data center, then the design flexibility will be more. If it is internet based protocols which is used, then this flexibility, design flexibility will be less. So, how to design this inter data center networking is going to be an important paradigm to understand how different vendors like Google, Microsoft and Amazon, they are handling this kind of inter data center networking. Let us see the Microsoft. Microsoft says that it is very expensive resource with amortized annual cost of hundreds of millions of the dollars is only spent here in this kind of networking, achieving high utilization with software driven wide area network. There is a paper which was published in ACM SIGCOMM 13. Now, let us see what are the traditional approaches of wide area network approach. So, the traditional approach to the traffic engineering in such network use the MPLS, that is multi protocol label switching. This is the protocol for wide area network which is used as a de facto standard, that is a traditional approach. So, the networks with several sites spread over defined area connected to each other, perhaps over the long distance fiber links. So, let us see about the protocols which are required to connect this inter data center networks. So, often they use the link state protocol to flood the information about the network's topology to all the nodes. So, at the end of each protocol, every node has a map like this, and then flood available the bandwidth information for traffic engineering, also spread the information about the bandwidth usage on each of the different links in the network. So, given that there is already traffic flowing in this network and some of the links will have the spare capacity, but do not. So, spreading this information just for traffic engineering will be too much of overhead. So, both IS and OSPF have an extension that allows the flooding of available bandwidth information together with their protocol messages. Third important thing is fulfill the tunnel provisioning requests. So, knowing the set of networks, when the router receives the new flow set request, it will set up a tunnel along with the shortest path on which enough capacity is available. It will send the protocol messages to the router on the path setting up its tunnel. Further, the MPLS also supports the notion of priorities. Thereby, if high priority flow comes in with a request for a path, lower priority flow might be displaced. So, these flows might then use high latency and higher cross paths through the network. Now, fourth one is that it will update the network state and the flood information. So, after the flow is assigned a terminal, the routers also update the network state. So, when the data packet comes into the ingress router, the router looks at the packet's header and decides what label that is, what tunnel this packet belongs to. Then it encapsulates this packet with that tunnel's label and send it along the tunnel. So, the egress router then decapsulates the packet, looks at the packet header again and sends it to the destination. In this scheme, only the ingress and egress routers read the packet headers. So, simple forward along the path. So, making forwarding along the path is very simple. This is the region, the protocol is called multi protocol label switching, MPLS. So, also MPLS can run several different protocols as long as the ingress and egress router understands that particular protocol and map into the label. That is why the name is multi protocol label switching. Now, let us see that using MPLS, what are the problems and inefficiencies we are going to get into the data center, inter data center networking. So, let us understand about the problems can we do, or we have to now, or these different vendors like Google, Amazon, how they are doing it, that inter data center networking. So, the problem one says that inefficiency. So, the first problem is inefficiency in terms of usage of the expensive bandwidth. Typically, this network would be provisioned for the peak traffic. Now, here at this image shows that if you have the traffic over the time, y axis utilization provision the network for the peak traffic. Now, the mean usage of the traffic might be very small. In this example, it is 2.17 times smaller than the peak. So, what you see over here is that means if provisioning the network only with the peak traffic, and most of the time the traffic is peak to the mean ratio is only 2.17 times. So, that will be a kind of wastage of the network resources by provisioning based on the peak traffic. So, that accounts to inefficiency in design of the wide area network software driven. So, therefore, achieving high utilization with the software defined wide area network was the theme of the paper which was published by the Microsoft in designing the inter data center networking at the Microsoft. So, here what we see that most of the traffic is actually the background traffic with some latency sensitive traffic as well. So, you can provision for the peak of the latency sensitive traffic and then fill the gap with the background which is not the latency sensitive traffic. So, here you can understand that to deal with this particular peak, what you can do is that this particular peak can be taken up as the background traffic. You can see that this particular peak is now divided here as the background traffic. So, if you remove this particular peak over the time, because this is not the latency sensitive, they are not the latency sensitive traffic. So, they will be put in the background, and with a non background traffic, that is latency sensitive traffic, will be provisioned here after adaptation. So, again I am showing you what are the different measures are achieved in high utilization of the bandwidth and thereby saving the cost in running the inter data center networking on the public, that is wide area network. So, most of the traffic is actually the background traffic with some are the latency sensitive traffic if you analyze the traffic. So, you can provision the peak of the latency sensitive traffic and then fill the gap with the background traffic which is not the latency sensitive traffic. So, you can now classify the traffic into the latency sensitive and non latency sensitive. So, latency sensitive traffic, the peak of the latency sensitive traffic is going to be useful, and then the remaining capacity can be filled by non latency sensitive traffic, and it is called the background, with the background which is not the latency sensitive. So, looking up the traffic which is coming into the data center, it can be classified into latency sensitive and non latency sensitive, and thereby just saying that the peak. So, we are now going to see that the peak of the latency sensitive traffic will become important measure for resource provisioning in for planning about this particular method in inter data center networking. So, unless you differentiate the traffic by service, you cannot do such an optimization. So, it is not easy to do with the MPLS approach, because it does not have the global view of what services are running into the network. So, what parts of the network they are using and such. Also, the related point is that regardless of whether they are multiple services or not, MPLS, the routers make local greedy choices about the scheduling flows. So, the traffic engineering is suboptimal in MPLS. For these reasons, such a network run around 30% utilization to have enough headroom for these inefficiency, and that becomes too expensive in running the businesses for the cloud such as Google, Amazon, and the Microsoft. The second problem is inflexible sharing. Another big problem with the MPLS approach is that it only provides the link level fairness. So, at any link the flows can share the capacity fairly, but this does not mean that the wide area network wide fairness is ensured. For example, we have green flow sharing capacity across the length with the red flow. That is what is shown over here. So, both are shared. But with the blue and the green flows, both get capacity half the red flow. Blue and green, they get half of the red flow. So, red flow will get half of this, half of this. So, and they will get half of this and half of this traffic. So, we have the link level fairness, but we do not have the network wide fairness in MPLS. So, the network wide fairness is hard to achieve unless you have a global view of the network. So, therefore, let us see what kind of methods which were adopted here for wide area network traffic engineering. So, cutting edge wide area network traffic engineering TE, which was published by Google's work, that is called Google B4 method. So, B4 says that experience with globally deployed software defined network, software defined wide area network, and Microsoft on the other side has published his own way of software driven wide area network with high utilization, achieving high utilization in its Microsoft Swan paper that was published in ACM SIGCOMM. Both of them were talking about same thing, how to achieve the software driven wide area network and high utilization, that is called traffic engineering. So, let us go ahead and see what are the different aspects covered in their design of inter data center networks, which is going beyond what MPLS can give, which is only 30% of the utilization. With 30% utilization, these companies are unable to run these data center, because that becomes 70% will be overhead, going unnecessary waste of utilizing the public infrastructure, that is the bandwidth. So, let us see about the leverage service diversity. Some tolerate the delay. To get very high bandwidth utilization wide area network because of the natural fluctuations over the time. So, to leverage the diversity in the services, some services need certain amount of bandwidth at a certain point of time, and they are inflexible, and some other services can use to fill in wherever room is left over. For example, latencies instead of queries. So, centralized traffic engineering can only be possible with the help of software defined network, and the technologies are such as open flow. So, software defined networking approach gather the information about the state of the network, make the central decision about the flow of the traffic, and then push those decisions down to the lower level to actually implement them. But bringing all the information together in one place is relatively complex decision. So, let us see how we are going to do this software defined networking using traffic engineering, using this particular model where it is not easy at one place to get this entire global information. Then third one is that exact linear programming is too slow. So, traditional optimization technique like linear programming, which is a way to take the set of constraint on a required amount of data flow over the parts of the network and come up with an optimal solution, but to apply it to the situations where we need make relatively quick decisions So, part of the complexity comes from multitude of the services, the different priorities. So, if you have one service, we could run the flow algorithm and that would be much faster. So, it required something faster if it is not guaranteed to be exactly optimal. So, this particular way linear programming is too slow and we require some other faster methods. Now, fourth important aspect is that a dynamic reallocation of the bandwidth. So, the demands on the network change over the time. So, to make continual decisions about what traffic is the highest priority to move across, which links at a given moment, is a challenge with linear programming to make quick decisions. So, these are all online algorithm, but they are not online in the same as things inside the data center might be. For example, Google runs its traffic engineering 500 or so times a day. So, it is not a fine grained as the things we might need inside our data center. So, traffic between these facilities is relatively stable, it seems. So, the demand on the network change over the time. So, make it continual decisions about what traffic is high priority to move across the links at a given moment is a challenge with the linear programming to make quick decisions. So, the online algorithms, but they are not online in the same way as the things inside the data center might look like. Now, fifth one is called error rate limiting. So, the commonality in the architecture is to implement enforcement of the flow rates. So, when the traffic enters into the network and will do that at the edge rather than at every hop around the path. So, let us see B4's B4, that is Google's wide area network design that was published in 2011. So, Google's B4 was the first highly visible software defined network success, that is software defined network in wide area network application. Now, this is a private wide area network connecting Google's data center across the planet. So, Google in 2011 published in the paper that it has 12 locations spread across 3 different continents, which is shown over here. So, you can see that Google's B4 considered worldwide deployment, that Google's data center are located 12 different locations across 3 different continents, which are shown here in the world map. So, you can see so these are 12 different locations. You can see that India is not figuring out here in this particular data centers. So, across 3 different continents, and it has a number of characteristics that such as massive bandwidth requirements deployed to the modest number of sites, elastic traffic demand that seek to maximize the average bandwidth, and full control over the edge servers and the network, which enables the rate limiting and demand measurement at the edge. So, here you can see the warehouse scale computer facility WSC network. So, here this is a Google data center, Google edge, then carrier ISP edge, then carrier ISP edge, and then Google data center at different locations, and all these things are there. So, again the characteristic is that massive bandwidth requirements deployed to the modest number of sites. So, although there are only 12 sites, but lot of bandwidth is required in elastic traffic demand that seeks to maximize the average bandwidth and full control over the edge servers and the network, which enables rate limiting and demand measurements at the edge. So, what happens at one site, one data center is shown over here. Now, Google's B4 view at one site. So, inside one site it has it has the data center network of clusters and border routers. So, here you can see that it is a wide area network, and here eBGP routers will be there, cluster border routers, and data center network is there, and wide area network routers are there, which will be running IBGP and ISIS to the remote sites. So, in the traditional settings, these are connected using eBGP to run the routers, which would then also interface with IBGP or ISIS to the other data center sites. For finer control over the routing, this will be moved to the software router, that is the software switch that runs on the server. The interface is with OpenFlow to set up the routing rules, and that particular software switch will run the routing protocols between the cluster borders and also other sites, and then OpenFlow uses the routing information from the software switch and forwards the rule to the in the wide area network router. So, therefore, it has a software control and the traffic engineering server, which manages what rules exactly are installed. Let us see this in this figure. So, here you can see that this is the data center and cluster border routers, which runs eBGP, and where this software switch, and here you can see that it runs the traffic engineering over this kind of server, and these are the wide area network router, which are now enforcing the traffic engineering with a software based control. So, the traffic engineering server collects the topology information, the available bandwidth information, and has the last information about the flow demand between different sites. So, the traffic engineering server pushes out the flow allocations to different data center at the data center with a multiple controller, then enforce these flow allocation to the data center. So, you can see that traffic engineering server will collect all the information from different sites and then enforce and then enforce these flow allocations to these particular data center. Now, what are the design choices? So, BGP routing is considered as a big switch. So, it also keeps available the BGP forwarding state, because each of their switch allows them to have multiple forwarding table. At the same time, they can afford to have the BGP forwarding table. So, in addition, the traffic engineering, if the traffic engineering scheme does not work, they can discard the routing table and use BGP forwarding state instead. So, the BGP routing table serves as a big red switch in their topology. So, that hardware is the custom and cheap and quite simple. In 2011, there were not many software defined network switches on the market. So, Google built their own using the cheap commodity equipments, and the software is smart with the safeguards, and most of these smarts are resides in the software. The switches are simple in the software, which is OpenFlow control logic at each side replicated for fault tolerant using Paxos. Further, for scalability of these systems, they use hierarchy of the controller. Software solution achieve nearly 100% utilization and solves the trafficking problem in 0.3 seconds. So, you can see that utilization increases from 30% to 100%. So, hierarchy of controllers is being used. So, at the top level, we have a global controller, which is talking to the SDN gateway. So, the gateway can be brought off as super controller, which talks to the controllers at all these different data center sites. Each site itself have multiple controller because of the scale of these particular networks. This hierarchy of controllers then simplifies things from the global perspective. So, this is an architecture P4 architecture overview. So, here you can see there are a global gateway and central traffic engineering server, and at every site different controllers are there, and there are different site controllers. At site A, this controller will have this software switch, and then it will be having the fault tolerant system, that is called Paxos, and similarly at the site B controller and site C controller, they are all connected with the gateway, and through the gateway the central traffic engineering server will be working along with that. Once this control plane decides the decision based on the requirements of the bandwidth, then these decisions will be forwarded here in the switch hardware at different sites. So, at site B switch, it is shown that with IBGP the decisions are being forwarded, and it is able to optimize the bandwidth usage or the traffic using the traffic engineering. So, the aggregation, that is flow groups and link groups. So, earlier the traffic engineering at the global scale is not at the level of mutual flows, but of flows of the group, but that also helps scaling. Further, each pair of the sites is not connected by one link, and so there are massive capacity links that are formed from the trunk of several high capacity links. All of these are aggregated and exposed to the traffic engineering layer as one logical unit. It is up to the individual site to the partition traffic, multiplex and demultiplex traffic across the set of links. Let us see the Microsoft's SWAN view. So, Microsoft has publicly disclosed the design of optimizing wide area traffic flow in their wide area network. So, the interesting feature is to make changes to the traffic flow without causing congestion, and here we can see the design, the architecture of Microsoft SWAN, which was published in ACM SIGCOMM as a paper, achieving high utilization with software defined wide area network. So, let us see some of the important things which is not there in Google's B4 system. So, Microsoft SWAN can say that it can think of different ways to do this, but we always going to run some link that may get used by both loads at the same time. So, take a look at the design of SWAN. There is an approach to making those updates with a certain amount of spare capacity, so that congestion can be avoided. This approach can take optimization one step further, so that providing a pretty strong guarantee on the lack of congestion even when the traffic data flow is changing. So, you can see that if this particular way the flow A is running and flow B is running, and you can see that if flow if it is changing, then it is going to now share this particular link FA. So, FA will not get that kind of capacity. So, in that way you can see that if you change the flows, let us say that flow FB is running between R2 and R3, and R1, R2 and R1, R4 and R3 flow A runs, then both will be satisfied here in this particular case. So, this is an optimization with at the level of flow, and it will also avoid the congestion while the network data flow of changing. So, conclusion in this lecture, we have discussed geo distributed cloud data center, interaction of data centers with the user and other data center we have brought about, and also we have shown that various data center internetworking requires design of software defined wide area network techniques, and we have also covered the techniques which is in the traditional wide area network, that is MPLS, and then Google's B4 way of designing the wide area network using software defined network, and Microsoft SWAN optimization of traffic engineering we have seen here in this particular slide. So, let us summarize that this particular cloud edge system not only requires the data center of some form, but also the inter data center network becomes quite substantial in running these kind of services. So, we have discussed here one such example how the inter data center network, that is called software defined wide area network for traffic engineering to achieve high throughput, that is beyond 30%, which is achieved through MPLS. So, with this, let us conclude this particular lecture. Thank you.